Salam sejahtera and greetings to both of my panels, Dr. Muhammad Zamani and Dr. Nur Razia. So my name is Laun Kumar Nalakianasekaran, and today I'm going to present about my final year project, which is about implementation of single money exchange of die method, which is also known as SMED or SMED, to reduce the setup time of the terminal lead welding machine. So my project is supervised by Prof. Maria IR Dr. Lo Cheng Yi. So actually, my project is based on a real problem of a manufacturing industry where I was introduced to a company called TDK Electronics Malaysia, located at Kawasan Perintis Center Brown at Johor Bahru through RECIP program. RECIP stands for Research Enhanced Structured Internship Program. So one of the problem in the production department of the TDK company is one of their machine called as the terminal lead welding machine has a high setup time or changeover time. So in this presentation, I will be explaining about the SMED method, which is the background of the study of my project, and the objective of my case study, problem statement, scope, and the expected outcome from my project, and also how I'm going to solve this real problem of the company by implementing SMED method. What is SMED? As I said before, SMED stands for single minute exchange of die. So SMED is a process or system that for dramatically reducing the time it takes to complete equipment setup or changeovers. So the name single minute exchange of die comes from the goal of reducing changeover times to the single digit. For example, less than 10 minutes. So moreover, SMED is created and developed by Dr. Shigeo Shingo. He's a Japanese industrial engineer, where he first implements the SMED method on a 1,000-ton press at Toyota Motor Company, where he successfully reduced the setup time of the ton press from 4 hours to 1 hour 30 minutes initially in just 6 months, and then under 3 minutes after a further 3 months. So as in a nutshell, I can conclude that SMED is a proven tool to reduce the setup time of a machine. So why we need to implement this SMED? So to answer this question, let me give an example of a process of changing a car tire. So we may change a tire in 15 to 20 minutes, but by implementing SMED method, a Formula 1 pit crew can achieve the same process of changing 4 tires actually in just 1.82 seconds to 4.5 seconds. So as example, as you can see in this video, a Red Bull pit crew employs several SMED techniques, such as doing everything they can before the pit stop begins, using a coordinated team, performing multiple roles simultaneously, and creating a highly standardized process. So the reduction of time in pit stop in F1 races is one of the beautiful concept or example of SMED. Setup time is the non-production time in which changeover or setup takes from one part to another. So, if, for example, if there's a machine that produces product A and product B, so after producing product A, a machine need to be set up with some adjustment and some settings to in order to produce product B. So the time of the last good piece of product A and the first good piece of product B is called as setup time. So in this setup time, there will be activities going on. For example, activities like cleaning, setup, adjustments, and trial runs. So in order to reduce setup time, so one of the examples that I can give, as you can see in the first picture, a man is going down and he's picking up the bricks to place on the wall. And the second picture shows the same simplified process by placing the bricks on a trolley, and the man pick from there very fast and place it on the wall instead of wasting time in going down to pick up the bricks. So this is how setup time is being reduced. So moving on to the case study of my project, as I said before, my case company for this project is TDK Electronics. It's previously known as AppCos. So the company develops and manufactures and markets many types of electrical components and system under the product brands of TDK and AppCos, focusing on fast-growing leading-edge technology markets. And the second picture shows the machine that I said before, which is the terminal lead welding machine, which has the highest setup and changeover time. And this machine also known as auto count impulse and MF. MF stands for medium frequency welding machine. So there are two methods of welding, which is impulse and medium frequency welding. So this is the inside view of the terminal rig welding machine, where the machine consists of two welding station on the left hand side, and also on the right hand side, which is known as station 6 and station 7. So the process that happens in this machine is actually is the terminal rig welding machines, where there are two different welding methods. One is medium frequency, another one is impulse. So the products that have been produced from this machine is two types of two electrode gas tube arresters. So the raw materials that will be inserted to the machines are the printed arresters and the wires. So the printed arresters will be loaded into the tube loading station, and the wires will be put into the wire loading station or the vibrating ball. So so this is the end product of the machine. The first product is a blue color two electrode gas tube arrestor, which should be welded using medium frequency, and it's actually coated by T. And the second one is actually coated by copper, which is the red two electrode gas tube arrestor, which should be welded using impulse method. I'll be explaining about the main activities that happens during the setup process or changeover process of this terminal rig welding machine. So the first activity, which is the initial activity, is to select the welding method. So there's only two welding methods, which is impulse or medium frequency. So it's actually selected by using the sub power switch, as you can see in the picture. So after that, we need to turn off the clamp 16 and the clamp 17. The clamp 16 and the clamp 17 is the one which hold the electrode and the electrode clip, which I will show it in the next slide, in the upcoming slides. So the buttons will be turned off to avoid the current passing through the clamp. Main activity 2 is the air cool cable or jumper position changing activities at both stations. So so the cable will be changed from the upper part of the bus bar to the lower part of the bus bar. So this is where the current will be transferred from the bus bars to the air cool cable and then to the electrode to create a spark to weld the wire onto the gas tube arrestor. Moving on to the main activity 3, the main activity 3 is about changing the electrode and electrode claim for each changeover. So every changeover, the electrode will be changed, shown in the picture. The main activity 4 is actually the wire adjustment activities. The wire from the vibrating ball will go through the wire clamp. So the main activity 5 is actually the welding pressing adjustment. So this should be done because each product, as I mentioned before, each product needs different pressure of welding. So moving on to the main activity 6. Main activity 6 is about the adjustment of the electrode and electrode claim, where the electrode and electrode claim should be perpendicular to each other. Main activity 7 is about the press run activities on both stations. Main activity 8 is about welding these changing activities. It's optional activities. It actually depends on the welding strength of the gas tube arrestor. Last but not least, the main activity 9 is to load the tubes on the load tube loading station and finally start the production. So all these main activities contains sub activities which have been clearly described in the draft report. So the problem statement of my case study is, as I showed, all the processes and the main activities of the setup process or the changeover process is almost 2.5 hours, which is very long, and all the activities are performed internally, which means the internal activities are done when the machine is stopped, and the machine need to undergo frequent changeovers because of its electrode claim is always worn off and need to be replaced. The objective of my case study is actually to study the existing changeover or setup process of the terminal welding machine. And my second objective is to propose a new standard procedure by simplifying the steps that I showed before, the main activities, especially in the existing changeover or setup process using the SMED approach. And the final objective is for sure to reduce the changeover or the setup duration from 2.5 hours to 1 hour by applying the SMED techniques. The scope of this project is where the study is carried out at the production department of the case company, which is the TDK Electronics. And secondly, the study will be focused only on one terminal rig welding machine, which is labeled as a C3 at TDK Electronics. And the third scope is this study focuses to reduce the setup time on the terminal rig welding machine by implementing SMED method. Last but not least, this study is expected to reduce the complex, time-consuming, and non-value-added activities in the case company. So my expectation from this case study is to identify the case company problems and ways, and also help the company to improve the production and the productivity of the machines, and also to promote the use of lean tools such as the SMED method and the value stream mapping, root cause analysis, and process flow charts in manufacturing industry. And last but not least, I believe that my case study will be a reference material related to production improvement in Malaysia manufacturing industry. This is the methodology of my project. So starting from selection of the machine and moving on to the data collection, data is collected through interview observation and document review, and all the data has been analyzed by using value stream map and root cause analysis. Then, if there's an opportunity for improvement, SMD method will be applied on the terminal link machine. So and follow with the implementation and experimentation. So if the target time achieved, which is bringing down 2.5 hours to 1 hour, another data analysis will be conducted to do a comparison between the target time before SMD has been applied and after SMD has been implemented. Value stream map, the time study has been done based on the data collected through the interview and the observation. So the data value stream mapping is enables to create a detailed visual representation of all steps in the work process. So as you can see in this map, the most time-consuming activities are actually manual welding, which is the test run activities. Another one is the electron flame adjustment activities, and electron flame changing activities, and also head cable jumper bushing changing activities. So this value stream mapping is done in this study on the terminal welding machine to actually provide a clear picture of the setup and changeover process in the machine, and also to visualize how long each setup and changeover process in the terminal welding machine is actually takes. So the next step is the root cause analysis, which is the fishbone, or also known as the Ishikawa diagram. So the root cause analysis is to determine the underlying causes of the machine in order to identify and implement the most effective solution. So the root cause analysis is actually a component of a broader problem-solving process and an essential component of continuous improvement. So based on this root cause analysis, the most problems is actually occur from the method they applying on the machine. So this is my SMED proposed methodology. My methodology is actually based on the literature review that I did. It's based on of course, based on the Shingo's SMED methodology and Macintosh changeover improvement. So it consists 5 stages. So stage 1 will be the setup process map and the mapping of the current state, which is already done in this FIP1. So the action is actually to analyze how setup tasks are executed in the current machine. And the method that should be applied is to videotape the entire changeover process that's happening on the terminal welding machine. So the outcome will be where we can determine the standard time for each activities that happening on the current changeover. So the stage 2 is to recognize the external and internal process steps. So to identify this, we should observe and work from the videotape to create an order list of elements. So the method is actually to study the video. So from there we can manage to recognize what work is performed and how long the element takes to complete and what tools are used to perform the work. So and the next stage is actually to separate the external work and internal work. So external work is the work that have been done to the machine when it was running, and internal work is the activity has been done to the machine when the machine is stopped. So this should be classified into 2 groups as internal activities and external activities, and this can be done by having a checklist, and the outcome will be the task group can be formed and their total time can be identified easily. So stage 4 is to shift the internal work to external work wherever it is possible. So it's like to modify the equipment and discarding some settings. So this can be done by using the SolidWorks software to redesign some parts of the machines. So and the methodology is also can be done by using the ECRS chart, which is the eliminate, combine, rearrange, and simplify. So by doing this, the outcome will be like we can manage to prepare operating conditions in advance. So last but not least, the stage 5 is to streamline all other activities and parallelism of the present activities. So the action is actually to combine some of the activities which can be made parallel and those activities visible also. So the outcome will be like we can manage to reduce the setup time when we combine some of the activities that possibly can be done. So this figure is showing the summarizing of the SMED methodology starting from the changeover and to spread the changeover to external, and converting all the internal activities to external, and finally streamlining all the activities. So this is the Gantt chart for my FIP1. So that's all from me. Thank you.